Hello, my name is Shahriar Shahriari, and this is a lecture in a series on general topics in undergraduate mathematics. This particular lecture is on inverses of functions. The main question is which functions have inverses, and we have a nice theorem that we want to prove. Given a function, f, it has an inverse if and only if it's one-to-one and onto. If you have two sets, how do we define a function? A function is a rule that assigns to every element of x one element of y. Each element of x gets one element of y. And the way we think of a function is as a map, as something that sends things over. X is called the domain, y is called the codomain, and what f does is gives you a rule for how to take elements of x and send them over to y. Every element of x needs to be assigned some element of y. Not all elements of y have to be assigned elements of x, and different elements of x could go to the same place. If you have a rule sending points x into y, then if it happens to be that some point in x is sent to multiple points in y, then you don't have a function. On the other hand, if 2 points go to the same point, then the function is not one-to-one. A one-to-one function is a function that different points go to different places. No two different points go to the same place. Sometimes these two things are confused. A function is something that does not send one point to several points. A one-to-one function is a function that does not send two different points to the same point. And a function is not onto if there's something in the codomain in y, something like delta, that's not hit by anything. That's not at the image of any point. So to be onto means that everything in y is the image of something in x. So what's function composition? If we have two functions, f and g, and f takes elements of x and sends them to y, so the domain of f is x and the codomain is y, and g has domain y and codomain something else z, then we can combine these functions. F takes elements of x and gives you elements of y, and g can take that result and then send it over to z. And that's what we call the composition of g and f. So when we write g circle f, we're talking about one function, a function that you first do f and then you do g, and the resulting function is called the composition of f and g. It's denoted by g circle f. In a previous lecture, we proved that if you have two functions and you have to have the codomain of the first function be the same as the domain of the second function, then if both functions are one-to-one, so is the composition. And if both functions are onto, then so is the composition. And as a result, if both of the functions are bijections, so is the result. What's a bijection? Functions that are one-to-one and onto. Bijection is also called one-to-one correspondence. For this lecture, we have a different question. We've got a function that maps elements of x to y, maybe one-to-one, maybe onto, maybe not. And our question is, what if we didn't like where we send that one element and we wanted to go back? We wanted to undo what we did. Can we undo the operation? A function that returns us back to where we started is called the inverse function. Such a function may or may not exist, but if it does, that's the inverse of our original function f. To define it more formally, recall what the identity map is. Our functions aren't necessarily from reals to reals, and they don't necessarily have formulas attached to them. We're thinking of a function as a rule that sends elements of the domain to the codomain. They don't have to be about numbers. So x is an arbitrary set, any set you like, and the map that goes from x to itself and sends everything to itself, it's a very boring map, the map that doesn't really do anything, is called the identity map. The identity map on x. To repeat what inverses are, we have a function f that sends every element of x to something. For example, it sends alpha to beta. The inverse function, if it exists, takes beta back to alpha, and it does that for every element of x and y. If I start with f, apply f to some element of the domain, and then follow that by g, I should be back where I started. That composition should be identity. But also, I want to be able to start at y and start with the function g and then do f and end up also in the same place. Either way, if you start with first doing g then f or f then g, you should be back where you started. This leads us to the formal definition of function inverses. If x and y are sets and you have a function from x to y, then a map g from y to x going the other way is called the inverse of f if g of f of x is x for all x in x, and f of g of y is y for all y in y. Such a function, if it exists, is called the inverse of f, and then we denote by f raised to the power minus 1. So f inverse is the name that we give it so that we don't have to keep saying g is the inverse of f. You could call it anything else you want. You call it Fred if you want. Another way of saying the same thing is to say that f and g are inverses of each other if G circle F, that's G composed with F, you do F first, then G, is the identity on the set X, and F circle G is the identity function on the set Y. So here's some examples. If you have the function that goes from R to R and defined by f of x equals x cubed minus 2, and G is the function defined by g of x cubed root of x plus 2, then maybe these functions are inverses of each other, maybe they're not, but we know how to check. We find the composition G of f of x, G circle F applied to x. I put G circle F in parentheses because I'm thinking of it as one function. So G circle F applied to x, that's G of f of x. Wherever I see x in the rule for G, G is cube root of x plus 2. Instead of that x, I put x cubed minus 2 because that's f of x. And when I do that and I do the algebra, I get x back again. So that's when I did f and then g, I got back where I started. And vice versa, if I do g then f, in the rule for f, wherever I see an x, I have to put g of x. F of x is x cubed minus 2. F of apple is apple cubed minus 2. F of g of x is g of x cubed minus 2. So it's cube root of x plus 2 cubed minus 2. And that's the same as x. So this says that G is F inverse and F is G inverse. In some ways, the role of X and Y are switched. In functions from R to R, where you have a formula, you would start with the original function and say, okay, Y equals X cubed minus 2. Instead of F of X equals X cubed minus 2, you say Y equals X cubed minus 2. Then you switch the place of X and Y because you want to go the other way. And then you solve for the new Y. You would get X equals Y cubed minus 2. From that, you would get Y cubed is X plus 2. And then Y is cube root of X plus 2. That's how you would come up with this. But you can't do that if you have functions from R2 to R3, for example. Let's say that the function from reals to reals, you feed real numbers into this function and comes out a real number, is defined by your favorite function f of x equals x squared. Is square root of x the inverse for f? First of all, just saying square root of x is inverse, I haven't really defined for you what the function is. I have to tell you what the domain and the target set are, what the domain and the codomain are, before I have told you what a function is. I can't say g goes from R to R because if g of x is square root of x, I can't plug in minus 2. This function does not have its domain the real numbers. I could define g to be going from non-negative real numbers to R because those are the numbers that I can plug in square root and get a real number. I could define it that way, but this is not an inverse for f. And why is that? Because if you apply f to minus 6, you will get 36. And then if you apply g to it, you get 6. Square root of 36 is 6. It's not plus or minus 6. These two functions are not inverses of each other. But if we had defined f and g, both of them, as functions from non-negative reals to non-negative reals, then f was x squared and g was square root of x, then they would have been inverses of each other. The moral of the story is that whether or not something is an inverse of another thing does depend on how you define the codomain and the domain. The codomain of the first function has to be the same as the domain of the second one, and their composition either way has to give you the identity function. The function f, you can define it, f of x equals x squared. The biggest domain you could define it is all of reals. You can plug in any real you like. But if you do that, then that function doesn't have an inverse. Square root of x is not an inverse for it. But if you limit the domain and say you could plug in negative numbers, but I'm not going to do that, I'm going to keep the domain to be non-negative reals, then for that function, the function whose domain is non-negative reals, and its image is non-negative reals, if you think of it that way, then that function does have an inverse. The main question that we want to ask is which functions have inverses? And we have a nice theorem that tells us exactly which functions have the inverses. F is a function and it has an inverse if and only if it's one-to-one and onto. It has to be both of those. And if it is, then it has an inverse. If it's not, it doesn't. This is if and only if, which means we have to prove two directions. If f has an inverse, then prove that it's both one-to-one and onto, and assume that we know that a function is one-to-one and onto, and prove that has an inverse. For the first direction, we assume that we have a function f that has an inverse, and that inverse is g. We have to show that it's both one-to-one and onto. So even in this one direction, we have to prove two things. We have to show that it's one-to-one and onto. How do we prove something is one-to-one? Whenever you want to prove one-to-one, you assume that two things went to the same place, and then do one of two things. Either assume those two things were different, and they went to the same place, and then you get a contradiction, or you don't prejudge whether they were the same or not, and you say two things went to the same place, and then you show that after all, they were the same thing. And if you can do that, then the function is one-to-one. If you can't do that, maybe that will guide you to an example to show why in this situation the function is not one-to-one. So we are assuming that f of x1 equals f of x2, and then I'm going to somehow prove that x1 and x2 are really the same. What is f of x1 and f of x2? Those are elements of y, because f applied to x1 and x2 ends up in y. And so what can I do with that? I can apply g to them. They're both the same element of y because f sent x1 and x2 to the same place. So f of x1 is the same as f of x2. G is a function, can't send that thing to two different places, has to send that thing to one place. So g of f of x1 is g of f of x2, but g of f of x1 is just x1, and g of f of x2 is x2. Why? Because g circle f is the identity map, because g is the inverse of f. And that says x1 equals x2, and I just proved to you that f is 1 to 1. So now how do I prove f is onto? To prove onto, you pick some arbitrary element of the codomain. You pick something in y. Beta is arbitrary. It's not your favorite element, not the one you like, but just some element in y. And then you have to find an alpha in x such that when you apply f to alpha, you get beta. You can't just say f sends alpha to beta. You have to tell me which alpha. X has a whole bunch of elements in it. You have to come up with what element alpha I'm assured that goes to beta. And in this case, we define alpha to be g of beta. Beta is in y. We're looking for its pre-image, what goes to it. So we take beta and apply g to it. We can do that because beta is in y. And g of beta is in x. And that's going to be the alpha that we want. But you might say, why is that? What does that alpha work? The proof of the pudding is in the eating. You just apply f to it to see what happens. If you apply f to alpha, you get f of g of beta. But f of g of beta, because f circle g is the identity, if you do g and f, we get back where we started, that's beta. So f of alpha is beta, the map is onto, because we found a particular alpha that hit that beta. We have shown that if a function has an inverse, it's both 1 to 1 and onto. Now the other side, if the function is 1 to 1 and onto, why does it have an inverse? We have to now construct an inverse. We have to say, how do I come up with this function that's the inverse for f? I need to define for you a function from y to x, and this is how I do it. You give me an arbitrary element of y, and I have to tell you what g of beta is. That's how you define a function. And so I say, give me something in y. So you give me beta. What do? I'm going to tell you what g does, but I'm going to go back to what I know. And f I know is onto, so there must be some element in x whose image is beta. That element is alpha. And because f is 1 to 1, I know that there's no ambiguity. There's just exactly one element that goes to beta. That's the element that g will send beta to. You're looking for where to send beta. You get the help of f. You say that f is sending something to this guy, exactly one thing. G is going to send this back to that. As soon as you do that, beta is mapped by g to the unique element in x that f maps to beta. If you start with something in x and apply f to it, then if you apply g to it, why do you get back to where you started? Because that's the way you define g. If you take alpha, send it to y by f, then g will automatically, by its definition, send it back. If you start with g and an element of y and see where it goes, then where does f send it? F send it back to that element because g already checked where f is sending things, and it sends that element exactly to the place that if you apply f to it, you're back where you started. So that's why you have inverses. So we proved that a function has an inverse if and only if it's 1 to 1 and onto. A corollary is if you start with a 1 to 1 onto map, then the inverse is also 1 to 1 onto. The proof is pretty straightforward. If f is 1 to 1 onto, it has an inverse, f inverse. But f inverse has an inverse, f. Because it has an inverse, it's 1 to 1 onto by the theorem. So I'm using the theorem twice. Once to say that f has an inverse, and the other to say that f inverse, because it has an inverse, it's 1 to 1 and onto. I'm done with talking about functions in general. I want to show you two examples how these bijections, 1 to 1 onto maps and inverses come up in a combinatorics problem and in a group theory problem. In combinatorics, often we use bijections to show that two sets have the same size. If you have two sets x and y, and if you find a bijection, a 1 to 1 onto map, then that means that you're pairing elements of x and y. For every element of x, you have exactly one element of y. This guy is matched to that one. This one is matched to that one. This one is matched to that one. This one is matched to that one. F is pairing each element of x with exactly one element of y. In this situation, we say x and y have the same cardinality. If x and y are finite, then to say that they have the same cardinality is the same as saying they have the same number of elements. If x has 10 elements, then y will have 10 elements because we just matched all of the elements. If x and y are not finite, then they're infinite. For infinite sets, we still can have bijections, and that's when we use the word cardinality. The next video in this sequence will explore that. In combinatorics, we're less interested in that. We're interested in the case when x and y are finite. If you have a bijection between two sets, then you know that they have the same size, and this is used in counting problems often. Often you want to translate a problem from one situation to another, to a more familiar situation where you can count easier. And so you want to say how many elements are in here. You want to say they're the same as here, and the way you show that is a bijection, and then maybe you know how to count that second set, and then you know how many elements are in the first set. Let me give you an example of that. This example appears lots of places, including in my book, Invitation to Combinatorics. Let's say that 48 people are sitting in a room, and one of them is you. You have someone in front of the room list all the possible committees that you can have with an odd number of members. So committees of size 1, not much of a committee, but a committee nevertheless. Maybe actually you get more done if you're just a committee of 1. Then committee of size 3, 5, 7, and so on, all the way till committees of size 47. The list will have every one of those committees, lots of possibilities for committees. Now, someone in the back of the room will list all the possible committees with an even number of people. So 2 people, 4 people, 6 people, but also 0 people, a committee with the empty set, and also the committee of the whole, which includes everyone. You don't have to include those if you don't want, but then the answer to the question will be slightly different. The question is, which list is longer? That's a combinatorics problem. We have this list here and that list here of all odd committees and even committees, and we want to compare them. We can use bijections. Let A be the set of all committees with even number of members. Those are the guys in the back of the room. And B, the committees with odd number of members. Those are the committees that are listed in front of the room. I want to specify one of the 48 people. Maybe you were in that room, so alpha is you. I'm going to define a function from A to B. A, remember, is not a committee, is the list of committees that have even number of members, and B is the list of committees that have an odd number of members. And I'm going to define a function that goes from A to B in this peculiar way. If you take a committee that has an even number of people, then see if you are a member of it or not. If you're not a member, join it. If you are a member, leave it. By doing that, I will change the parity of the size of the committee from even to odd. So A is an element of script A, is a committee with even number of elements. And if you take you out or put you back in, depending on whether or not you were not or were in there, A now will have either one fewer or one more element, an odd number. It's a well-defined function in the sense that if you feed to this function a committee with an even number of elements, a committee with odd number of elements comes out. For example, if you give it the empty set, you'll get the committee that has just you in it. Or if you give it the committee that has everybody in it, then you get the committee that's everybody but you. So we do have a function from A to B. Now the question is that is F 1 to 1 and on to. One way to deal with that is to define G from B to A just like F. So if you have a committee with odd number of members, then get a committee with even number of members, again, by taking you in and out, depending on whether or not you were in there. And these two functions are inverses of each other. If you put yourself in the committee and then take it back out, you're back where you started. If you take yourself out and back in, you're where you started. It's clear that F is the inverse of G. And because F and G are inverses of each other, they're both bijections. So we have a bijection. We could do this more generally. If you start with a set with n elements and look at the number of subsets of even size and the number of subsets of odd size, they're always the same. Let's talk about the connection of this to group theory. If you have an arbitrary set, I like to call it omega, then in group theory, we sometimes call perm omega, permutations of omega, to be the set of all bijections from omega to omega. This, for example, is what I use in my book, Algebra in Action. A bijection is a one-to-one onto map, but you can think of it as a permutation, switching around the elements of omega. You're permuting elements. If you have two one-to-one onto maps, we have shown that their composition is also a one-to-one onto. This was done in the previous lecture. And if you have 3 functions, the composition is associative. If you find F circle G, then circle H, you get the same thing as if you do F circle G circle H. And the reason is that all you're doing is you're doing these functions in succession. Both sides are F circle G circle H, meaning you apply H, then G, then F. It doesn't really matter which 2 you combine first. F circle G is certainly not the same as G circle F. We talked about that in the previous lecture. But F circle G circle H is the same as F circle G circle H, because we're not changing the order, but we're changing which two are we going to combine first? The first property in group theory, we say that's closed under this operation. And the second property, we say that the operation is associative. What operation? Function composition. And we have the identity function, which in group theory plays an important role. It has the role that if you compose it with any function, you get that function back again. And what we have just proved today is that every one-to-one onto function, every bijection has an inverse. That was the purpose of this lecture, to prove that every permutation, every bijection from omega to omega has an inverse. This set perm omega is closed, it's associative, has an identity, has inverses, and that's exactly what the definition of a group is. A group is a set, in this case, all bijections from omega to omega, and an operation, in this case, function composition, that satisfies these four properties. And so permutation of omega is a group. In the case where omega is finite, you can take omega to be a generic set of size n, and then perm omega has a different name, Sn, the symmetric group of degree n. Elements of Sn are permutations of n things, different ways that you can permute n things. I'm going to end with an example of that. S3 is the bijections from 1, 2, 3 to itself. How many of those are there? Where can you send the element 1? You can send it to 1, 2, or 3. So you have 3 choices. How many ways can you send 2? 1 went somewhere. So one of those is already taken. So there's 2 choices for 2 and 1 choice for 3. So that's 6 choices. These are exactly the same as permutations of 3 objects. And there are 6 permutations of 3 things. But what are the elements of this? These are 3 of them. The identity. F, for example, says 1 to 2, 2 to 3, 3 to 1. I wrote F squared for this guy because if you compose F with itself, this is the one you get. You get 1 goes to 3, 2 goes to 1, 3 goes to 2. You also have 3 other ones. G, which is just switching the place of 1 and 2. If you compose your F circle G, you get the function that switches 1 and 3 and keeps 2 fixed. If you compose F squared with G, you get the function that switches 2 and 3 and keeps 1 fixed. In group theory, you should go to the lecture on the symmetric group in my group theory lectures as part of Algebra in Action series of lectures. We use a different notation. We use the cycle notation in group theory. In combinatorics, we often don't use the cycle notation. We might use a 2-line notation or something else for permutations. This is the end of this lecture. Like my video if you liked it. Subscribe to my videos if you like to be subjected to more math videos, and keep hydrated at all times. I will see you at the next lecture.